Good evening. My name is Okwesilieze Wadoka, an intern under S2P Africa, and I'm going to be presenting a project that I did with my partner, Chidozie Chikaume, and it's titled The Parametric Design and Simulation of a Fan Impeller. The aim of this project was to create a fan design that can compete with the existing designs in the market, with the objectives of creating a parametric 3D model of the existing fan models in the market, carrying out simulations to compare these existing models, creating a new fan model, optimizing the geometry and material in the new fan model created, and then finally comparing the new fan model with what we have in the market. So now these are two different fan designs, fan impeller designs. The one on the left is an older design, probably very popular 15 years ago, 10 years ago. And the one on the right is what you find in market as at now, 2021. And the aim of this project, and a peripheral aim of this project rather, was to observe or to understand the trend in the change of the design. And beside each of these models, you can see there are 3D models, both created with the Fusion 360 API using Python programming language. And I'm going to be taking you through the process of the creation of these 3D models. So first of all, the helical profile was created. This helical profile was basically a surface loft between two helixes. A helix is what you would commonly say is a spring shape. So the shape of a spring is what you know as a helix. So a helical profile was created by simply lofting two helixes of variable diameters. Secondly, the edges of the fan blades were created by using two helixes and a semicircle. This was so as to create a closed profile in order to intersect the helical profile created. A hub was created and also the fan impeller. After getting the existing models, two stages of simulation were undertaken. The first stage was the CFD simulation, and the second stage, the static stress simulation. The CFD simulation was done so as to understand why the geometry and the number of blades had changed. And then the static stress simulation was done so as to understand why there was a change in the material used in these fan impellers. These are the conditions for each simulation. On the left, we have the CFD boundary condition. And on the right-hand side, we have the static stress loading condition. For the CFD simulation, the parameter looked at was the velocity, maximum velocity along the axis of rotation. And for the static stress simulation, the parameter looked at was the minimum safety factor at the point of failure. Now, these are the geometric parameters for each of the fan models. Again, on the left-hand side, for figure 9, we can see the older fan blades, and then on the right-hand side, we can see the newer fan blades. And these are the CFD results. We can see that it's quite obvious to us why there was a change in the geometry and blades, geometry and number of blades, because for the newer fan blades, you can see a maximum velocity of 4 meters per second. And for the older fan blades, you can see a maximum velocity of just 2.97 meters per second. And then for the static stress simulations, you can see for both scenarios, a very high factor of safety. So now, what does that tell us? We have 4 things. First of all, it tells us that the geometry of the blades play a very huge part in the velocity of the air at the outlets. And also that the stresses acting on the blades are minimal when compared to the strength of the materials used, which makes sense for the change in material, because if plastic is going to be performing just as well as aluminum, and the best engineering choice to make is to choose plastic because it is cheaper and it is lighter. In creating the new fan blades, 4 stages of simulation were done. The first stage was done to determine the optimal span angle. The second stage was done to determine the optimal edge curvature. The third stage to find the optimal blade angle, and the fourth stage, the optimal impeller blade number. Now, the first stage, span angle. For this, on the left-hand side, we can see the parameters used. The span angle was varied from 15 degrees to 90 degrees in steps of 15. Again, this was made possible because of the fact that the Fusion 360 API was used, not the GUI. On looking at the results, we can see that the optimal span angle was 45 degrees. Moving on to the next stage of simulation done, the degree of edge curvature. This edge curvature is mainly affected by a parameter known as distance between turns. So that is the parameter we have on the x-axis of our results, the graph results. And we can see that the optimal distance between turns is 75 centimeters. Moving on to the third stage of simulation, the blade angle. The blade angle was varied from 10 degrees to 50 degrees in steps of 10. Why didn't we exceed 50? Because we needed the fan blades to remain axial and not become radial. And we discovered that the optimal blade angle was 30 degrees. Finally, the number of blades. We tested 3 blades, 5 blades, and 7 blades. And we discovered that 3 blades was the optimal number. And then we compared our design versus the best design in the market. And we discovered that our design has beaten the design in the market. By looking at the legends, you can see that our design achieves a maximum velocity along the axis of rotation of 5 meters per second, whereas the best fan in the market achieves that of just 4 meters per second. In conclusion, not only have we created a new product, but then this demonstration shows us that this can be used in engineering education for 3D modeling, fluid dynamics, strength of materials, and what have you. And this allows us to connect theory taught in the classroom with real life applications, and hence we've created products.